I'm going to talk about some joint work with John Fraser. And now, Marston's theorem, I think, was mentioned twice this past week. So I think this is number 3, but I could be wrong. Marston's theorem says that we take any Borel set, any Borel set on RD, and we choose a direction to project that set. And it says, well, for almost all choices of directions, the projection will have house of dimension as large as possible, being the dimension of the set X or 1 if the dimension of X is very large. So when we say almost all, what we're saying is that the set of directions for which this does not happen, so when we have here a strict inequality, is a set that has Lebesgue measure 0. So the next question from this is, well, what's the dimension of this set? And we ask this question in a bit of a more general setting. Instead of working only with the minimum, we just ask for the house of dimension of the set of directions for which the projection is smaller, the dimension of the projection is smaller than this number u, where u can be between 0 and this number. Now, this question was first asked by Kaufman in the 60s, and he gave this bound of u. So for sets X in R2, he said that this set has dimension less than or equal to u. And this bound happens to be sharp when u is equal to the house of dimension of X. That means that there is an example of a set X for which when we put u equal to its house of dimension, we get equal to the house of dimension of the set X. Later, this has been, lots of people worked on this, but then the next result I'm going to talk about was given by Bergen in 2010 and Overlin in 2012. So Bergen actually proved something a bit stronger, but Overlin's proof is simpler, and he just proves this. That for sets on R2, if we put u equals to dimension of X over 2, then this is a 0-dimensional set. So the bounds that we have are, we have 0 between 0 and dimension of X over 2, and then we have the sharp inequality when u equals the dimension of X, we get the dimension of X. And of course, we have here the bound u that's given by Kaufman here. But now when looking at this graph, it seems like we should be able to get some continuity here, some continuous bound. And that was conjectured by Overlin in 2012, and it was proven in the paper by Ren and Wang in 2023, which was also mentioned several times in the conference. So they proved that this is a bound for the exceptional set direction for the dimension. So now I'm gonna switch and talk about something else for a bit. If we take the Fourier dimension of a set is defined in this way. So it's take a set X, look at the measures in the set, calculate the Fourier transform, and see how they decay at infinity. So we take this L infinity norm, weighted L infinity norm, and we take the supremum over all the polynomial decays. That's the Fourier dimension of the set. And the Fourier dimension is always a lower bound for the house of dimension. Now, talking about projections, what we get for the Fourier dimension is that for absolutely all projections, all directions, the Fourier dimension of the projection can be larger than the Fourier dimension of the set. So in particular, when we take the dimension of the set to be less than 1, we have this chain of inequalities. The Fourier dimension of the set is smaller than its projection. The Fourier dimension of any set is smaller than the house of dimension. And then the house of dimension of the projection is always smaller than the house of dimension of the set. So in particular, if the set has equal Fourier and house of dimension, which is called a Salem set, then all these inequalities become equalities. And the first one was valid for all directions. So then all these things are equal for all directions, and we have no exceptions for Marston's theorem. Now, this is also valid when the dimension is greater than 1, but I didn't write that case because it's just uglier. Equations are nicer in this case. But if the dimension of the set is greater than 1, then all projections have dimension 1. So more generally, if we take U to be less than the Fourier dimension, because of this, for any set, it doesn't matter if it has Fourier and Hausdorff dimension equal, we have an empty set for the exceptional set of projections for this range of U. And so going back to the plots that we have, this is Bergen and Oberlin, Ren and Wang and Kaufman. But if we add the Fourier dimension, then we get that if the Fourier dimension is less than the Hausdorff dimension over 2, this set is empty. And if the Fourier dimension is large and it's somewhere in there, then we get a huge improvement on the dimension of the exceptional set. And so if we just blindly apply Fourier dimension, we have like huge improvement. Because here before we were having some positive dimension, and now it turns out that the set is actually empty. So the question is, well, maybe I don't want to get something as strong as empty set. Maybe I want to get some better bound. And perhaps I can use the Fourier decay to get some improvement on this bound. So we're going to try and answer these questions. And the thing is, how do we measure this Fourier decay? We're going to answer this with the Fourier spectrum. We define the Fourier spectrum of a set. We fix some parameter theta between 0 and 1. And it's going to be the supremum over, so we take a measure and we measure the decay of the Fourier transform in this way. Now this looks a bit complicated, but if we set theta equals 1, we recover the energy integral that gives us the Hausdorff dimension. And if you've never seen that, then just don't worry. You can just think about this as some way of measuring Fourier decay. Now, some facts about the spectrum is that it's a continuous and non-decreasing function of theta, and it interpolates between Fourier and Hausdorff dimension. So for each theta, we always have these inequalities. When theta is 0, we recover the Fourier dimension. Theta is 1, we recover Hausdorff. So maybe the picture that you should have in mind is we start at some point at Fourier dimension of x. We have here the Hausdorff dimension of x. And if theta moves between 0 and 1, then we start here and it goes like this, for example. So that's the Fourier spectrum. And now regarding projections, we kind of get the worst of both worlds because we get something for almost all projections and for almost all directions, and we get the inequality that was given by the Hausdorff dimension. So the projections can be larger than the Fourier spectrum of the set. But we can get something just a bit stronger than this. We can get all directions if we just subtract something that depends on theta on this side. And so from this, since this is for all directions, we immediately get some, again, empty dimensional, empty set for the exceptional set for some range of U that depends on the spectrum. But again, we're interested in having something weaker than empty set. We want just another bound that depends on the Fourier spectrum. And these are the bounds known for Hausdorff dimension. We have the 2U minus dimension of x by Ren and Wang that I mentioned at the beginning. And then for higher dimensions, we have, depending on if the set has small or large dimension, we have these two bounds. And using the Fourier spectrum, we can get this other bound here. And so now the question is this bound any good? I mean, now we have some bound that depends on U, on the Fourier spectrum, and on theta. And we want to see for some sets, this bound is actually better than some of this. If we just do the inequalities, then for Ren and Wang's inequalities, so for R2, we draw this Fourier spectrum for the set, depending on if it has dimension less than 1 or larger than 1, if it just that plot happens to intersect these shaded regions, then we have improvement on Brennan-Wang inequality, and the same for higher dimensions. We should have some different shaded regions. So we can improve in this case for dimension of X less than 1, we can improve Matila's bound, or Perez and Schlag's bound when the dimension of X is larger than 1. And just to finish, an example on higher dimensions, we can take the product of 3 Cantor sets with different parameters alpha, beta, and gamma. And here we can see that the Fourier spectrum, and this is the Fourier spectrum at theta equals a half. So the bound that we get from the theorem at theta a half gives us this red line here, which for some parameters of U is better than Matila's and Perez and Schlag. And now this line, this red line is for theta equals a half, and the theorem was an infimum over all theta. So this is actually an upper bound for the actual bound that we have from the theorem. So that would be all. Thank you.